Imagine you are standing in a field at dawn. The air is cool, and the light is coming in low and golden across the grass, and everything is still and quiet and ordinary. And then the ground moves. Not like an earthquake, not like something sudden and violent, but like a slow, deep pulse beneath your feet. The way the earth presses back when something truly enormous is walking toward you. And before you see it, you feel it. And then you look up, and you keep looking up, and you keep looking up, because the thing coming toward you out of the tree line is tall enough to look down into the second floor of a building, and long enough that its tail is still in the shadows of the forest, while its neck is already curving out over the open meadow ahead of it. And the sound it makes as it walks is not a roar, not a scream, but a slow, massive, rhythmic percussion. The deep thud of legs like stone pillars making contact with the earth. Each footfall landing with a weight you do not just hear, but absorb. And you understand, in a way that no photograph or museum skeleton has ever quite communicated to you, that this animal is not a fact you were taught. It is a force. It is a presence. It is something the world was once designed to contain, and it is not designed for the world you live in now. The largest animal that ever walked the surface of this planet was a dinosaur. Not a whale, not a prehistoric elephant, not a mammoth or a giant sloth or any of the remarkable megafauna that shared the Pleistocene with our ancestors. A dinosaur, a long-necked, small-headed, slow-moving plant-eating giant that belongs to a group called the sauropods, and that reached body masses so extreme, lengths so staggering, that even the scientists who study them spend considerable time simply trying to believe the numbers their own measurements produce. We are talking about animals that may have weighed as much as 70 or 80 tons. Animals that were longer than 3 school buses parked end to end. Animals whose single vertebrae, the individual bones of their backbones, were taller than a grown adult human being standing upright. Animals so large that they represent a kind of upper boundary on how big a land animal can possibly get before the physics of the world simply refuse to cooperate any further. And they are gone. They have been gone for 66 million years, wiped out along with all the non-avian dinosaurs when an asteroid approximately 12 kilometers across struck the shallow sea that is now the Yucatan Peninsula of Mexico, releasing energy equivalent to roughly 10 billion atomic bombs in a single instant, and ending the Mesozoic era in fire and darkness and cold. The sauropods went with everything else. The last one fell somewhere in what is now North America or South America or Asia, and its bones slowly mineralized into stone over millions of years, and the world moved on without them. But what if it had not? What if the asteroid had missed? What if by some small adjustment of trajectory, some fractional degree of deviation in the cold silence of space, the bolide that ended the age of dinosaurs had passed harmlessly by, and the Mesozoic had continued, and the sauropods had lived, and the world we know today had been built around creatures of that almost incomprehensible scale? What would that world look like? What would it sound like? What would it feel like to exist in it? And what would the largest dinosaur that ever lived, still walking the Earth today, mean for the ecosystems, the landscapes, the very geology of a planet that evolved alongside it? That is what we're going to explore tonight. Slowly, carefully, with all the rigor the science demands and all the wonder the subject deserves. We are going to rebuild the world these animals lived in, understand them from the inside out, and then, step by careful step, we are going to imagine what would have had to change and what would have stayed the same if the extinction never happened and the giants walked on. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you are tuning in from. I always love seeing how far these stories travel. Now dim the lights if you have not already. Take a deep breath and let the modern world fade away. We should begin where the animals themselves began, because understanding what a sauropod was, biologically and ecologically, is the only way to understand what it would mean for one to still exist. And to do that, we need to go back, much further back than the Cretaceous extinction. Back to a time when the sauropods were not yet the giants they would become. Back to the Triassic period, to a world so different from our own that even the continents would be unrecognizable. The Triassic began approximately 252 million years ago, in the immediate aftermath of the greatest extinction event in the history of life on Earth. An event called the Permian-Triassic extinction, or sometimes simply the Great Dying. In the Great Dying, somewhere between 90 and 96% of all marine species and approximately 70% of all terrestrial vertebrate species were eliminated, most likely by a combination of catastrophic volcanic activity in what is now Siberia, ocean acidification, and a runaway greenhouse effect that pushed global temperatures to levels near the edge of what complex life can tolerate. The world that emerged from the other side of that event was largely empty. The ecological niches that had been filled for hundreds of millions of years were vacant, and life, as it always does, began to fill them. In the early and middle Triassic, the dominant land animals were not dinosaurs. They were the archosaurs, a broad group of reptiles from which both dinosaurs and crocodilians would eventually descend. And the therapsids, the mammal-like reptiles that would eventually give rise to the mammals themselves. The first true dinosaurs appear in the fossil record around 230 to 240 million years ago, in the late Triassic, and they were not particularly impressive. They were small, bipedal, lightly built animals, quick on their feet, filling the ecological role of small and medium predators and omnivores in a world still dominated by other groups. You would not have looked at them and thought, here is the future ruler of the Earth. You would have looked at them and thought, there is a reasonably successful small reptile living in the shadow of larger things. But the Triassic-Jurassic extinction event, which occurred approximately 201 million years ago, changed the balance of power again. Another mass extinction, again probably triggered by massive volcanism. This time in what would become the central Atlantic region as the supercontinent Pangaea began to crack apart, cleared away many of the archosaurs and therapsids that had been competing with the dinosaurs for ecological space. And into the vacuum, the dinosaurs expanded, rapidly by geological standards. Within a few million years of the Triassic-Jurassic boundary, the dinosaurs had diversified enormously, and among the groups that emerged in this early Jurassic explosion of diversity were the ancestors of the sauropods. The earliest sauropodomorphs, the broader group to which sauropods belong, were not yet the giants. Animals like Plateosaurus, which lived in the late Triassic of what is now Germany and Switzerland, were already reasonably large by the standards of their day, perhaps 6 to 10 meters long and weighing a few hundred kilograms. And they were already experimenting with the body plan that would define the group. Long neck, small head, relatively large body, teeth designed for processing plant material rather than meat, but they were still partly bipedal, still able to rear up onto their hind legs, still compact enough to move through a landscape in the way that most animals move through landscapes. The true sauropods, the fully quadrupedal, column-legged, enormously long-necked giants, emerge in the early Jurassic, and from there the story of their evolution is largely a story of getting bigger, not continuously, not in a straight line, but with a general trend across tens of millions of years toward increasing body size. That is one of the most sustained examples of directional evolution in the entire fossil record. By the Middle Jurassic, roughly 170 million years ago, sauropods like Mamenchisaurus in what is now China were already reaching lengths of 25 meters or more, with necks that made up more than half of their total body length. By the late Jurassic, the classic sauropod fauna of North America, the animals that most people think of when they think of the word dinosaur were in full flourish. Brachiosaurus, with its giraffe-like proportions and upwardly inclined neck. Diplodocus, one of the longest animals ever to exist, its whip-like tail stretching out behind it for meters. Apatosaurus, heavy and powerful, built like a locomotive draped in scales. And then, in the Cretaceous, the final act of the sauropod story before the asteroid ended it, came the titanosaurs. The word titanosaur is not hyperbole. It is taxonomy, the scientific name for the last major radiation of sauropods, a group that diversified extensively across the southern continents during the Cretaceous period and produced, in the final 30 or 40 million years before the extinction, the largest land animals that have ever existed. We know them from bones discovered in Argentina, in Patagonia, in the arid badlands of the Neuquén province, where a remarkable series of excavations beginning in the 1990s and continuing to this day have produced specimens of staggering dimensions. Animals like Argentinosaurus, known from partial vertebrae and limb bones so large that single elements must be moved with heavy equipment. Animals like Patagotitan maiorum, described in detail in 2017 from a more complete specimen, estimated at around 69 tons and approximately 37 meters in length. Animals like Notocolossus and Dreadnoughtus and Futulonchosaurus, each of them pushing the boundaries of what bone and muscle and tendon can be asked to do, each of them representing a different answer to the question of how large a land animal can actually get. It is Patagotitan maiorum that most paleontologists currently consider the strongest candidate for the title of largest known dinosaur, though the science is genuinely unsettled and new discoveries continue to challenge old assumptions. A cast of its skeleton is on permanent display at the American Museum of Natural History in New York, and it is so large that the animal's neck extends out of the main gallery and into the hallway beyond. If you have stood in that gallery and looked up at it, you already know something that no photograph quite prepares you for. And if you have not, then try to imagine standing at the base of a 5-story building and tilting your head back to look at the roof. That is roughly the view from below a Patagotitan's neck. But weight is not just a number when it comes to these animals, it is an engineering problem of the highest order. And understanding how evolution solved that problem is the key to understanding whether a living sauropod is even physically possible in the modern world. Because the honest answer before we even begin the thought experiment of placing one in our current landscape is that keeping an animal this large alive required a set of biological innovations so extraordinary that we are still working out how they functioned, even now with all the analytical tools modern science can bring to bear. Start with the skeleton. A sauropod's vertebrae were not solid bone throughout. If they had been, the skeleton alone of an animal like Patagotitan would have weighed far more than the animal could have carried. Instead, the vertebrae of large sauropods were highly pneumatized, meaning they were riddled with internal air spaces, connected to a system of air sacs that extended through much of the body cavity. This pneumatization is something sauropods share with modern birds, and it is not coincidental. Both birds and sauropods are archosaurs, and both evolved the same solution to the same problem from the same ancestral starting point. A pneumatized bone is dramatically lighter than a solid bone of the same size, and across a skeleton of hundreds of bones, the weight savings are enormous. Some estimates suggest that pneumatization reduced the skeletal mass of large sauropods by 30 to 40%, compared to what it would have been if the same bones had been solid. The neck is the part that most demands explanation. Diplodocus had a neck approximately 6 to 7 meters long. Mamenchisaurus had a neck somewhere in the range of 9 to 12 meters, depending on the specimen and the reconstruction. And various other sauropods occupied every point along that spectrum and beyond. A neck this long is a mechanical challenge of the first order. It must be long enough to reach food sources far above, or spread across a wide horizontal area. It must be light enough not to collapse under its own weight. It must be flexible enough to be useful, but stable enough to support the movement of food and air and blood through its length. and it must be connected to a body large enough to contain the muscles and organs that keep the whole system running. The solution evolution found was elegant. Sauropod neck vertebrae were extraordinarily long relative to their width, sometimes 10 or 15 times as long as they were tall, but deeply pneumatized, hollow in a way that removed mass without removing structural strength. The neck muscles were not arranged the way you might imagine, not like a crane cable pulling the head up from directly above, but in a complex fan of ligaments and muscles running along and through the vertebral column, in a way that allowed the neck to be supported with far less muscular effort than a naive estimate would suggest. Some researchers have proposed that the longest sauropod necks functioned somewhat like a fishing rod, held in a roughly horizontal position by tension through a passive ligament system, and requiring relatively little active muscular effort to maintain. This would explain how an animal could hold its neck out for hours at a time without exhausting itself, which any animal that must spend most of its waking hours eating in order to fuel a body of that size absolutely had to do. Which brings us to the feeding. An animal the size of Patagotitan, weighing somewhere between 60 and 80 tons, would have needed to consume an almost incomprehensible quantity of plant material every day simply to maintain its body temperature and fuel its metabolic processes. Modern estimates based on metabolic scaling relationships and comparisons with large mammals suggest that a sauropod of this size might have needed to eat somewhere in the range of 300 to 500 kilograms of plant material per day, every day, without stopping for very long, because an animal with this caloric requirement cannot afford extended periods without feeding. The long neck was not merely an adaptation for reaching high into trees, though it was certainly that. It was also, and perhaps more fundamentally, an adaptation for dramatically increasing the feeding radius of the animal without requiring it to move its enormous body. If you can sweep your neck through an arc of 30 or 40 meters around your body, you can clear a huge area of vegetation without taking a single step. And every step you take costs calories that must then be replaced. The neck is, among other things, an energy efficiency device at the scale of evolution. The digestive system of sauropods was something we can only partially reconstruct, because soft tissue does not fossilize in the way that bone does, and the interior of a sauropod's body cavity is therefore largely inaccessible to direct investigation. But we can make inferences. The teeth of most sauropods were not designed for chewing. They were simple pegs or spatulas, good for stripping leaves and needles from branches, but not for grinding plant material into a paste, the way a cow or a horse or an elephant would. This means the digestive breakdown of tough plant material happened almost entirely in the gut, aided by fermentation, probably by microbial communities, similar to those that help modern herbivores digest cellulose, and perhaps by gastroliths, smooth stones swallowed deliberately and retained in the stomach to help grind food mechanically. We have found smooth, polished stones in association with sauropod skeletons, which supports this interpretation, though the evidence is not entirely unambiguous, and the debate continues in the paleontological literature. The heart of a sauropod presents its own extraordinary challenge. To pump blood all the way up a neck that might be 10 meters long, to a head that might be held at a height of 15 or more meters above the ground in some species, against the full force of gravity, requires either an extremely powerful heart or a blood pressure so high that the vessels in the head would be at constant risk of rupture. In modern giraffes, the tallest living mammals, the heart is proportionally enormous and blood pressure is extremely high, and the giraffe's maximum neck length of around 2 meters is already near the physiological limit for the mammalian cardiovascular system. Sauropods had necks 5, 6, 7 times longer than a giraffe's. The physics of getting blood to the top of those necks is a problem that has occupied physiologists and paleontologists for decades, and the honest answer is that we still do not have a fully satisfying solution. Several possibilities have been proposed. One is that sauropods had multiple hearts along the length of the neck, booster pumps of a kind, a feature with no modern analogue but not biologically implausible in principle. Another is that sauropods carried their necks more horizontally than vertically most of the time, reducing the height differential between the heart and the head, and therefore reducing the cardiovascular demand. The horizontal neck hypothesis has gained considerable traction in recent years, supported by biomechanical modelling of the neck structures and by the observation that a horizontal neck position actually makes good ecological sense for many species, allowing them to sweep large areas of low-growing vegetation without raising and lowering the head constantly. A third possibility is that sauropods had some cardiovascular innovation completely unlike anything we see in living animals, a solution to the problem that we simply cannot recognize because we have no living reference point for it. The truth is probably some combination of all of these factors, varying across the many different species and body plans within the sauropod group. What is clear is that these animals solved the problem. We know they solved it because they existed, because their fossils are in the ground, because they were the dominant large herbivores on most of the world's continents for over 100 million years. Evolution does not sustain a failing design for 100 million years. The sauropod body plan worked. It worked extraordinarily well. It produced the largest land animals in the history of life. And if the asteroid had missed, if the Cretaceous had continued, there is every reason to believe the sauropods would have continued too, adapting and diversifying, perhaps growing larger still, perhaps exploring body plans we have not yet imagined, certainly remaining the ecological keystones of the terrestrial megafauna in a way that would have shaped every ecosystem on the planet. So let us say the asteroid missed. Let us say it was a near thing, close enough that the shockwave disturbed the upper atmosphere and caused a brief, cooling event, a volcanic winter of sorts, that lasted a few years and stressed the global ecosystem, but did not trigger the cascade of extinction that the actual impact caused. Let us say the non-avian dinosaurs survived. The tyrannosaurs and the ceratopsians and the hadrosaurs and the ankylosaurs and the pachycephalosaurs, all of them making it through that narrow window of geological time and continuing to diversify into whatever worlds came after. And among them, of course, the sauropods, the titanosaurs still walking the southern continents, the various lineages that had persisted into the late Cretaceous, still feeding, still breeding, still depositing their eggs in carefully chosen nesting sites, still moving through the Cretaceous landscape with that slow, inexorable, ground-shaking patience. What happens next? What does 66 million years of continued sauropod evolution look like? The honest answer is that we cannot know in any detail. Evolution is not a predictable process. It is driven by the specific environmental pressures of specific moments in time, by chance mutation, and by the particular genetic variation present in any given population, by the accidents of geography and climate and competition that determine which individuals reproduce and which do not. We cannot replay the tape of evolution and expect to get the same result twice, but we can make broad inferences based on what we know about evolutionary patterns, about the ecological roles sauropods filled, about the way large body size tends to evolve and persist in herbivore lineages, and about the environmental changes that would have occurred over 66 million years of a world without the Cretaceous-Paleogene extinction. The most important thing to understand is that the world itself would have changed dramatically, even without the asteroid. The Cenozoic era, the 66 million years since the extinction, has been a time of enormous geological and climatic transformation. The continents have continued their slow drift on the tectonic plates, India colliding with Asia to push up the Himalayas, Africa closing the ancient Tethys Sea to form the Mediterranean basin, the Americas connecting via the Isthmus of Panama and transforming ocean circulation patterns. Global temperatures have fluctuated dramatically from the warmth of the early Eocene, when palm trees grew in what is now England and crocodilians lived in the Arctic, to the cooling of the Oligocene and Miocene, to the glacial cycles of the Pleistocene that brought ice sheets down to the mid-latitudes of both hemispheres. Grasslands, which did not exist in the Cretaceous in any significant extent, evolved and spread across enormous areas of the continents, creating new ecological niches and transforming the energy base of terrestrial ecosystems. Flowering plants, which had already begun their extraordinary diversification in the Cretaceous, continued to expand their dominance over the global flora, changing the composition of forests and meadows in ways that would have had profound effects on the animals that fed on them. If you like the video so far, please leave us a like and a sub. A sub to the channel helps us make more videos for you to watch and keep the channel alive. In our world, all of these changes were met by the mammals, the descendants of the small, mostly insectivorous or omnivorous creatures that survived the extinction in the ecological shadow of the dinosaurs. In the absence of the non-avian dinosaurs, the mammals rapidly diversified to fill the empty ecological space, producing within 10 to 20 million years an astonishing variety of body forms and ecological roles. Whales evolved from terrestrial artiodactyls, horses evolved from small dog-sized browsers, elephants evolved from the small aquatic ancestors of the perissodactyls, and the large terrestrial herbivore niches that had been occupied by hadrosaurs and ceratopsians and ankylosaurs were filled by the various lineages of large ungulates, the horses and rhinos and cattle and deer and antelope, and by the proboscideans, the elephants and their extinct relatives, some of which reached body masses approaching 10 tons. In a world without the extinction, none of this happens. The mammals remain in the background, not because they are incapable of diversification. Their evolutionary potential was clearly extraordinary, but because the ecological space is occupied. The large herbivore niches are held by dinosaurs. The large predator niches are held by tyrannosaurs and their kin. The medium predator niches are held by dromaeosaurids and troodontids. The small insectivore and omnivore niches are held by a variety of small theropods and early diverging dinosaur lineages. In this world, the mammals remain small and ecologically marginal, the way they had been throughout the Mesozoic, probably diversifying somewhat as the world changes, but never getting the chance to occupy the large animal niches that their biology would have allowed. The sauropods in this alternate world face the same environmental challenges our mammals faced. Grasslands spreading, climates cooling, the supercontinents fragmenting, and the ocean circulation patterns changing. And they meet those challenges the way evolution always meets challenges, by dying in some lineages and diversifying in others, by adapting body plans and metabolic strategies and dietary preferences to the new conditions, by finding the available niches and filling them. We cannot know the details, but we can say with reasonable confidence that some lineage of sauropods would have persisted through the climatic fluctuations of the Cenozoic, because sauropods had persisted through the dramatic climatic fluctuations of the Jurassic and Cretaceous, and because very large body size in herbivores provides genuine ecological resilience. A large herbivore can eat lower quality plant material than a small herbivore, because it can retain food in its gut for longer and extract more energy from it before it passes through. A large herbivore can travel farther to find food when local conditions are poor. A large herbivore is less vulnerable to predation and more able to compete for resources. And so, in our thought experiment, 66 million years after the asteroid missed, there are still sauropods. They have changed, they have diversified, they have adapted to grasslands in some lineages, perhaps evolving different tooth morphologies or jaw structures to cope with the more abrasive silica-rich grasses that make up much of the global vegetation today. They have responded to the cooling climates, perhaps developing better insulation in some populations, or migrating along the corridors between continental landmasses as the geography of the world shifted beneath them. They are not the same animals that walked the Cretaceous, but they are recognizably sauropods, recognizably enormous, recognizably the ecological giants of every landscape they inhabit. And among them, somewhere in the grasslands and gallery forests and open woodlands of what we call South America, or Africa, or South Asia, there is an animal that represents the current upper limit of sauropod body size, the largest dinosaur alive today. In this imagined world, an animal that may not be as large as Patagotitan maiorum, because the conditions of the Cenozoic world, with its cooler climates and more seasonal vegetation patterns, may have selected for somewhat smaller body sizes in some lineages. Or it may be larger, because 66 million additional years of evolution in a world with available resources and no competing mammal megafauna is a very long time, and evolution has repeatedly produced body sizes far beyond what any observer would have predicted in advance. We simply do not know, but let us imagine it at a scale comparable to the largest Cretaceous titanosaurs. Let us imagine an animal perhaps 70 tons in mass, 35 to 40 meters in length, an animal that represents the absolute physical maximum of what terrestrial locomotion on this planet can sustain. What does that animal look like in the world we know? What adaptations has it developed for a Cenozoic landscape? The skin is the first thing you would notice, if you could stand close enough to notice anything before the sheer scale of the animal overwhelmed your capacity for detail. In the Cretaceous titanosaurs, we have preserved skin impressions from several species, particularly from South American forms, and what they show is not the smooth, elephant-like hide you might expect. Sauropod skin, at least in some species, bore small, irregular scales of varying sizes, sometimes with larger tubercles, raised bumps or nodules, scattered across the body, and in some areas the skin shows a complex mosaic pattern of polygonal scale shapes packed together like ceramic tiles on a floor. The skin of the modern titanosaur, having passed through 66 million years of further evolution, might look somewhat different. In a warmer environment, thin skin with rich vascularization, a network of blood vessels close to the surface, would help shed excess body heat, a significant concern for an animal that generates heat simply through the metabolic effort of being enormous. In a cooler or more seasonal climate, thicker, more heavily keratinized skin might provide some insulation. Some lineages in this imagined world might have evolved something analogous to the dermal osteoderms, small bony plates embedded in the skin that we see in some titanosaurs from the Cretaceous fossil record. Saltosaurus, a relatively small titanosaur from Argentina, had such osteoderms scattered across its back, and they may have provided some defense against predators, or some structural support for the weight of the skin itself, or perhaps both. The coloration of sauropods is something we cannot know from fossils alone. Melanosomes, the microscopic structures that produce color in feathers and some scales, have been preserved in exceptional fossil specimens, but mostly in small theropods with feathers, not in large sauropods. In the living animal of our thought experiment, color might serve any of the functions it serves in modern large animals. Camouflage, though effective camouflage, becomes increasingly difficult to achieve as body size increases, because there are fewer and fewer backgrounds large enough to hide behind. Thermoregulation, with darker colors absorbing more solar radiation and lighter colors reflecting it. Social signaling, with distinctive patches of color on the neck, flanks or tail serving as visual cues for species recognition, mate choice, or status display. The long neck of a sauropod would be an obvious candidate for striking visual display, given that it is the most visible part of the animal from a distance. And we see in modern long-necked animals like giraffes that the neck is indeed a site of social interaction and visual communication. The locomotion of an animal this size is something that paleontologists have studied intensively, using trackways, the fossilized footprints left by living sauropods in soft sediment, as their primary evidence. Sauropod trackways are found on every continent where the animals lived, and they tell a remarkably consistent story. Sauropods walked slowly. not because they could not move faster, but because speed, for an animal this large, is energetically very expensive and mechanically very dangerous. A 70-ton animal running at speed is a 70-ton object that must somehow stop and turn without destroying itself. The limb bones of large sauropods are thick and dense and arranged in a nearly columnar posture, with the legs held largely straight beneath the body like the legs of an elephant or a pillar, not bent at the acute angles we see in smaller, more agile animals. This posture is mechanically efficient for supporting enormous weight, but it limits the animal's top speed and maneuverability. Trackway analysis suggests that most sauropods moved at a walking pace of roughly 4 to 8 kilometers per hour during normal travel, with the larger species toward the lower end of that range. The footprints themselves are extraordinary objects. A large titanosaur footprint could be a meter or more in diameter, roughly circular or slightly oval, with toe impressions sometimes visible at the front. The rear feet are slightly larger than the front feet in most sauropods, reflecting the fact that the hind limbs carry somewhat more of the body's weight than the forelimbs. In areas where sauropods moved frequently, the repeated impact of those enormous feet would have compacted the soil, created persistent depressions, channeled water runoff, and altered the local vegetation in ways that were ecologically significant. In a world where sauropods still exist today, you would find their trackways written into the landscape in every place they regularly travel, paths worn into the earth by decades or centuries of repeated passage, muddy depressions at water sources where they gathered to drink, areas of bare compacted earth around favoured resting spots, and the subtle topography of landscapes shaped by the repeated footfalls of creatures whose weight concentrated enormous force into each square meter of ground. The sound of a large sauropod moving through a landscape at a walk would be, first and foremost, a sound felt as much as heard. The ground vibration produced by each footfall of a 70-ton animal would be detectable by seismic instruments at considerable distances, and by the sensitive mechanoreceptors in the soles of human feet at ranges of several hundred meters. The actual acoustic sound produced by the impact, the crunch and thud of a column of bone and muscle and fat meeting the earth, would be deep and resonant, like a bass drum of extraordinary size, felt in the chest more than heard by the ears. At close range, you would also hear the vegetation, the crack of branches too close to the path, the swish of undergrowth against the animal's sides and legs, the occasional rumble of the digestive system, which in an animal processing hundreds of kilograms of fermented plant material per day, would be audible as a low, continuous gurgling and churning from within the barrel of the torso. And the vocalizations. Here is something that surprises many people when they first think carefully about it. We have very good reason to believe that sauropods were not silent animals. The evidence comes partly from the structure of the inner ear, which can be reconstructed from the bony labyrinth preserved in fossil skulls, and which indicates sensitivity to sound in a frequency range consistent with low-frequency vocalizations. It comes partly from analogy with modern crocodilians and birds, the living relatives of the dinosaurs, both of which are vocal animals with complex acoustic communication. And it comes partly from the basic ecology of the situation. Large social animals in dense or forested environments, which is where many sauropods lived, have strong selective pressure toward acoustic communication, because visual signals are often blocked by vegetation and chemical signals dissipate quickly. Elephants, the largest living land animals, communicate extensively through infrasound, low-frequency vibrations below the threshold of human hearing, that can travel through both air and ground for distances of several kilometers. It is entirely plausible that large sauropods did something similar, using the resonance of their enormous torsos and the length of their necks as acoustic instruments for producing and possibly amplifying low-frequency calls. In a world where sauropods still exist, the acoustic landscape of any region they inhabit would be shaped by their presence. Not by loud, dramatic roaring, which is probably not what they did, but by the deep, almost subterranean vibrations of very large animals communicating across distances. The way the call of a blue whale is not loud in the sharp, percussive sense, but is overwhelming in the sense of mass and resonance and sheer physical power. You would feel a sauropod calling before you heard it, and you would hear it before you saw it. And by the time you saw it, you would already understand that this is an animal that does not need to announce itself with drama, because its scale does that work entirely on its own. Now let us think about what these animals would do to the landscapes they inhabit, because this is where the thought experiment becomes genuinely ecological rather than merely zoological. The largest living land animals today, the African bush elephant, reaching masses of perhaps 6 or 7 tons in the largest males, are already known as ecosystem engineers. Animals whose activities so profoundly alter the physical structure of their environments that entire communities of other species depend on the changes they create. Elephants knock over trees, opening forest canopy and allowing light to reach the ground. They dig for water in dry riverbeds, creating pools that sustain dozens of other species through dry seasons. They wallow in mud and create depressions that fill with water and become small wetlands. They disperse the seeds of many plant species in their dung over distances of tens of kilometers. The savanna ecosystems of Africa are partly shaped by the activities of elephants and the removal of elephants from those ecosystems, which has happened in many areas through poaching and habitat loss, causes measurable cascading changes in vegetation structure, species composition, and water availability. Now, scale up from 6 tons to 70 tons. Scale up from an animal that occasionally knocks over a tree to an animal that might simply walk through a forest and leave a corridor of fallen and damaged vegetation behind it. Scale up from an animal that digs a small hole to find water to an animal whose footprints, each a meter across and pressed into soft ground by 70 tons of overlying animal, create substantial depressions that fill with water and persist for weeks or months. Scale up from an animal that deposits a few kilograms of dung per day to an animal that may deposit several hundred kilograms. The ecosystem engineering effects of a sauropod-scale herbivore are not merely larger versions of what elephants do. They are qualitatively different, operating at a spatial scale and an intensity that creates ecological effects with no modern analog whatsoever. Consider the vegetation first. A group of large sauropods moving through a landscape would leave visible and lasting traces. The browsing height of a large titanosaur with a long neck, held at even a moderate upward angle, would reach 15 to 20 meters above the ground, accessing the canopy of all but the tallest trees. Any tree species within the sauropod's range would be subjected to browsing pressure at heights that no other herbivore could reach, which would favor trees with defenses against high browsing, whether chemical defenses like tannins and alkaloids, or physical defenses like very hard wood, or the concentration of leaves far above the browsing height in the upper canopy. It would also favor the coexistence of tall trees, because trees that could grow above the sauropod's maximum browsing height would gain a competitive advantage over shorter species. You might expect, in landscapes shaped by millennia of sauropod browsing, a bimodal distribution of vegetation, either very short ground layer plants that the sauropods walk over and around, or very tall trees that the sauropods can browse from the lower portions, but that invest heavily in growing above the accessible height. The middle height range, the shrubs and small trees that form the understory of many modern forests and savannas, might be heavily suppressed or absent in areas with high sauropod density. The soil disturbance effects would be similarly significant. A 70-ton animal exerts a ground pressure per unit area that depends on the size of its feet and the number of feet in contact with the ground at any moment. But even distributed across 4 large, broad feet, the pressure per square centimeter is substantial, well above the compaction threshold of most soils when the ground is moist. Regular sauropod movement through an area would compact the soil, reducing its permeability, altering drainage patterns, and changing the composition of the soil invertebrate community. At water sources, where large animals congregate and the ground is permanently moist, the compaction and disturbance effects would be extreme, potentially creating areas of bare, puddled earth surrounding permanent water bodies, like the mudflats you see around watering holes in African game reserves, but at a much larger scale and with much deeper impressions. The dung deposition is perhaps the most ecologically consequential effect of all. Plant material consumed and processed through the enormous gut of a sauropod would emerge transformed. Seeds within the plant material would either be destroyed by the digestive process or, in the case of harder seeds, passed intact through the gut and deposited far from the parent plant. A form of seed dispersal by gut passage that we call endozookery. In modern ecosystems, large animals are responsible for the long-distance dispersal of many plant species, whose seeds are too large or too heavy to be transported by wind or by small animals. The extinction of large mammals in the Americas at the end of the Pleistocene, animals like ground sloths and mammoths and horses, is thought to have dramatically reduced the dispersal of many plant species, whose seeds evolved for transport through large gut systems. In a world with living sauropods, the dispersal of plant seeds across enormous distances by animals that can travel 10 to 20 kilometers per day in the course of their normal feeding movements would shape the geographic distribution of plant species in ways that cascaded through every level of the ecosystem. And the nutrient cycling. A sauropod's dung is not just a pile of undigested plant material. It is a concentrated package of nutrients, extracted from the vegetation over a wide area and deposited in a single location. Dung beetle communities, which in modern ecosystems are extraordinarily diverse and ecologically important, would be structured around the enormous output of sauropod herds, fly communities, microbial communities, specialized plant species that thrive in the nutrient-rich conditions around large dung deposits. In areas where sauropods regularly rest or congregate, the soil chemistry would be measurably enriched, and the plant communities growing in those enriched soils would be different from the surrounding landscape, creating a patchwork of ecological variation at the scale of individual animals and their movements. All of this amounts to saying something that sounds simple, but is actually deeply important. In a world where sauropods still exist, the landscapes of that world are not just landscapes with very large animals in them. They are landscapes that have been shaped by the presence of those animals at every spatial scale, from individual meter-sized footprint depressions to regional patterns of vegetation and soil chemistry that reflect the cumulative activities of sauropod populations over thousands and millions of years. The land itself bears the imprint of the animals. The plants have evolved in response to the animals. The soils have been structured by the animals. Other species, from the largest predators to the smallest dung beetles, are organized around the ecological presence of the animals. Remove the sauropods and the ecosystem does not merely lose a species. It loses its organizing principle. It loses the force that created and maintained the very structure within which every other species has evolved to exist. This is what we mean when we say that a keystone species shapes its ecosystem. And sauropods, at their scale, would be keystones unlike anything alive today. Keystone species so large and so ecologically powerful that the entire architecture of the terrestrial world would be organized around their presence. Let us now think about the predators, because no discussion of the largest herbivores in history is complete without asking the question that everyone is already asking. What would be hunting them? And what would hunting them require? In the Cretaceous, the apex predators sharing the landscape with the large titanosaurs were the abelisaurids in the southern hemisphere, and, in some regions and time periods, carcharodontosaurids, very large theropod carnivores that reached body masses of 6 to 8 tons and lengths of 12 to 14 meters. These are extraordinary animals by any standard, the largest terrestrial predators that have ever existed, outranking even Tyrannosaurus rex in terms of raw body size. though probably not in terms of relative skull strength or bite force. They were not pack hunters in the cooperative sense we see in wolves or lions. They were almost certainly solitary or loosely associated hunters, or more accurately, opportunistic predators and scavengers, taking prey when the opportunity arose and feeding on carcasses when live prey was too dangerous or difficult to pursue. The relationship between a 12-ton predator and a 70-ton prey animal is not one of regular active pursuit and kill. It is not like a lion taking a wildebeest. The predator does not overpower the prey in any straightforward sense. Instead, if you like the video so far, please leave us a like and a sub. A sub to the channel helps us make more videos for you to watch and keep the channel alive. Instead, the relationship is more like that between a hyena and a hippopotamus, where the predator is capable of killing a juvenile or a weakened or injured adult, capable of driving a lone individual away from a carcass, capable of killing an animal that is already dying, but incapable of routinely dispatching a healthy adult in its prime. The vulnerability of the prey species is concentrated at the young, the sick, the injured, and the very old, and the predators exert their selection pressure through those vulnerable categories rather than through the ability to reliably kill the largest and healthiest individuals. In a world where sauropods still exist today, what plays the role of the abelisaurid? In our thought experiment, the non-avian dinosaur lineages survived the extinction and continued evolving for 66 million years. The large theropod lineages, the abelisaurids and carcharodontosaurids, might have continued on the southern continents, diversifying and adapting to the changing Cenozoic environments just as the sauropods did. Or they might have been replaced by later diverging theropod lineages that were better suited to the new conditions. The dromaeosaurid and troodontid lineages, which in our world's actual history gave rise to the birds, might in this alternate world have produced some lineages that retained terrestrial predatory lifestyles, while others took flight, diversifying in both directions simultaneously, the way many lineages diversify into specialists at different points along a continuum. Whatever the specific evolutionary history, the logic of the ecosystem demands that something fills the large predator niche in a world with sauropods. Because a population of 70-ton herbivores without effective predation would grow without check until it exhausted its food supply and crashed, and this boom-bust cycle would destabilize the vegetation and the whole suite of dependent species in ways that are ultimately bad for every participant. The predator-prey relationship is not merely a drama of tooth and claw. It is a regulatory mechanism that keeps the ecosystem in something like balance, preventing any single species from consuming its resource base faster than it can be replenished. The largest predators that exist in a sauropod world would be very large indeed, almost certainly larger than any terrestrial predator alive today, because the prey they hunt is so large that effective predation requires either great size or sophisticated cooperative hunting strategies, and probably elements of both. The behavior of sauropod herds in response to predation pressure is another area where we have some fossil evidence and a great deal of productive inference. Trackways show that sauropods sometimes moved in groups, with smaller individuals toward the center of the group and larger individuals on the periphery, a defensive formation analogous to what we see in modern elephants and muskoxen. The tail of a large sauropod, particularly in forms like Diplodocus where the tail was extremely long and slender at the tip, may have functioned as a defensive weapon, capable of being swung with enough force to injure or kill an approaching predator, and in some species possibly even capable of producing a supersonic crack at the tip, like a whip, creating a deterrent display. The sheer size of an adult sauropod would have been its primary defense. An animal weighing 70 tons and standing 5 meters tall at the shoulder has a great deal of mass to bring to bear against any attacker, and a predator that makes a mistake in its approach risks being crushed, kicked, or trampled with lethal consequences. Adult sauropods were probably not routinely hunted by anything, They died of disease, of accident, of old age, and their carcasses were then consumed by the predator and scavenger community in a process that could sustain a large number of animals for days or weeks. Because the amount of meat on a 70-ton animal is, as you might imagine, extraordinary. The eggs and the hatchlings were a different matter. Sauropods, like all dinosaurs, reproduced by laying eggs, and sauropod eggs, while the largest dinosaur eggs known, were surprisingly small relative to the body size of the parent. A large titanosaur laid eggs roughly the size and shape of a soccer ball or a bowling ball, because the shell of an egg must be porous enough to allow gas exchange for the developing embryo, and above a certain size, the shell becomes so thick that it can no longer be adequately permeable. This means that even the largest sauropod began life as a hatchling that could be held in a human hand, and spent the first years of its life growing from that tiny starting point toward the enormous adult size, passing through every intermediate size and therefore every intermediate vulnerability along the way. The mortality rate of young sauropods was almost certainly very high. The vast majority of hatchlings did not survive to adulthood. The ones that did were the product of both good genes and good fortune, and the good fortune component was very large in the early years, before the animal had grown large enough that predation risk dropped dramatically. The nesting sites of large sauropods would have been important landscape features in their own right. We have evidence from Cretaceous sites, particularly from Argentina and from Alca Mahuevo, an extraordinary nesting site where thousands of titanosaur eggs have been found in sediments that preserve not only the eggs, but in some cases the skin of the embryos within them. That large sauropods nested colonially, returning to the same sites repeatedly across many seasons, laying clutches of eggs in shallow scrape depressions, and then leaving them to incubate without parental attendance. The nesting colony would have attracted predators and scavengers from considerable distances, creating a seasonal concentration of activity around the nesting site that shaped the local ecology for the duration of the nesting season. In a world where sauropods still exist, these nesting sites would be among the most ecologically significant locations in any landscape, centers of biological activity and nutrient cycling that other species would have evolved to exploit. Now let us think about water. Large animals need enormous quantities of fresh water. An adult elephant drinks 100 to 200 liters of water per day during normal conditions, and more during hot weather or periods of high activity. A sauropod, with a body mass 10 to 12 times that of a large elephant, and with a metabolic system scaled to an animal of that size, would need correspondingly more water, potentially several hundred liters per day. The location of water sources would therefore be one of the primary determinants of sauropod distribution and movement patterns. Rivers, lakes, wetlands, and permanent springs would attract sauropods the way they attract large mammals today, but at a greater scale, and the impact of sauropod visitation on water sources would be far more dramatic than what we see with modern large mammals. The banks of rivers and lakes in areas frequented by sauropods would show heavy compaction and disturbance, with the large footprints filled with standing water, creating small ponds that persist between visits and support their own communities of aquatic invertebrates, amphibians, and the small reptiles that feed on them. Crossing rivers would present interesting challenges and opportunities for large sauropods. An animal of this size, walking into a river of moderate depth, would displace enormous volumes of water, creating waves and currents detectable far downstream. In shallow rivers, they might wade through with their feet on the bottom and their backs above the surface. In deeper water, they may have been capable of swimming or floating partially, using the buoyancy of their air-filled vertebrae and the air sacs in their body cavity to offset some of their body weight. There is some evidence from trackway sites where only the front feet are recorded in certain sections, suggesting that the animal was floating with its rear end buoyed up and was punting itself along with its forelimbs, the way an animal might swim in a river, where the bottom was within reach of its front feet, but not its rear. The crossing of rivers by large sauropod groups would have been spectacular events, visible from great distances and creating temporary changes in local hydrology and bank structure that would have been significant on the scale of the river ecosystem. In a world where sauropods share the landscape with our modern human civilization, all of this ecological activity takes on a very different character. The rivers and lakes that sauropods depend on for water are also the rivers and lakes that human communities depend on for water, irrigation, transport, and fisheries. The forests and grasslands that sauropods browse are also the forests and grasslands that human agriculture depends on for food production and the livestock grazing that produces much of the world's meat and dairy. The soils that sauropod movement compacts are also the soils that human farmers till and plant and depend on for the agricultural systems that feed 8 billion people. The collision between sauropod ecology and human civilization would not be a matter of occasional dramatic encounters. A dinosaur walking through a city, a sauropod crushing a car. It would be a matter of deep, pervasive, inescapable ecological conflict at every scale, from the local to the continental. Think about what modern Africa looks like in the areas where the largest mammals still exist in significant numbers. The Serengeti, the Okavango, the Kruger. These are places where the presence of elephants and hippopotamuses and rhinoceroses shapes the landscape visibly, where the ecology of the region is organized partly around the needs and activities of animals that weigh several tons. Now consider that even in those areas, the agricultural and ranching frontier has been pushing steadily inward, that the historic range of elephants in Africa has shrunk dramatically over the past 2 centuries, that the conflict between elephants and farming communities is one of the most intractable conservation problems in the world, precisely because an animal that needs to eat 300 kilograms of vegetation per day cannot easily coexist with a farmer whose entire livelihood depends on a field of maize or cassava or sorghum. A single elephant visit to a farm can destroy weeks of labor and months of food in a few hours. A single sauropod visit, an animal that eats 3 to 5 times as much as an elephant per day. And that is so large that a fence capable of stopping it would need to be built to specifications that most human communities could not afford, would be a catastrophe of a different order entirely. And yet, the coexistence of humans and very large animals is not an inherently impossible thing. We coexist with elephants today. We coexist with hippopotamuses, with large crocodilians, with tigers and lions and bears in the areas where those animals still have habitat. The coexistence is imperfect, marked by conflict and loss on both sides, but it persists. It persists because human communities have developed cultural and practical frameworks for managing the relationship, because governments have established protected areas where the large animals have priority, because the economic and ecological value of the large animals, through tourism and through the ecosystem services they provide, creates incentives for their conservation rather than their elimination. There is no reason in principle why a similar framework could not develop in a world where sauropods are part of the native fauna. It would require protected areas of enormous size, because an animal that may need to range over hundreds of square kilometers to find adequate food cannot be sustained in a small reserve. It would require buffer zones around agricultural land and economic compensation schemes for farmers whose crops are damaged by sauropod incursion. It would require a cultural accommodation of the kind that traditional communities in areas with large, dangerous animals have always developed. A knowledge of the animal's behavior patterns and seasonal movements. A set of practices for minimizing conflict. An acknowledgement that the world does not belong entirely to the human beings living in it. In some parts of the world, this accommodation would be more difficult than in others. In the densely populated agricultural regions of South Asia, or the intensively farmed areas of Europe or East Asia, the land use pressure is so extreme that there is very little space for an animal requiring the kind of range that a large sauropod would need. The populations of those regions would face a genuine and painful choice between the preservation of the sauropod and the agricultural systems that feed billions of people. It is the kind of choice that has, in our own world, generally been resolved in favor of the agriculture, with the large animals losing out almost every time. The tigers of South Asia and the elephants of South and Southeast Asia occupy a fraction of their former range precisely because the decision has repeatedly been made, implicitly or explicitly, that the land is more valuable for agriculture than for wildlife. But in other parts of the world, the accommodation would be more tractable. In the vast open spaces of sub-Saharan Africa, in the interior of South America, in the boreal forests and tundra of Northern Asia and North America, there is land enough, or there was land enough until relatively recently, to accommodate very large animals in significant numbers without immediate and total conflict with agricultural systems. These are the regions where, in our thought experiment, the sauropod populations would be most numerous and most ecologically viable, where the long continuity of their presence would have shaped the landscapes most profoundly, and where the human communities that share the land with them would have had the longest time to develop the cultural frameworks for coexistence. Imagine, for a moment, a pastoral community in the interior of what is now Brazil or Argentina, in the open grasslands and gallery forests of the Cerrado or the Gran Chaco. These communities, in a world with living sauropods, would have lived alongside the giants for as long as their cultures extend back into memory. Which is to say, for tens of thousands of years at minimum, because the evidence from paleoanthropology and genetics tells us that modern humans reached South America at least 15,000 years ago, and possibly considerably earlier. 15,000 years is a very long time. It is long enough for languages to develop elaborate vocabularies for the behavior and ecology of the animals that share your landscape. It is long enough for seasonal calendars organized around the migration and nesting and breeding cycles of the sauropod populations. It is long enough for stories and myths and religious frameworks to develop that accommodate the presence of animals so large that they must inevitably have seemed, to the earliest human observers, like something more than mere animals. The mythologies of many traditional cultures include what we might call thunder beings or earth shakers, powerful supernatural entities associated with the ground trembling and with forces beyond human scale. In a world with living sauropods, those mythological figures would have a clear and immediate referent. The thunder of a large sauropod herd moving across open ground would be felt as a seismic event before it was visible as a biological one. The sound would carry for kilometers. The ground would vibrate perceptibly at distances of a kilometer or more. Any community in the path of such a movement would know it was coming before they could see it, and the experience of waiting for something that large to appear over the horizon would be, by any account, a profound and frightening and awe-inspiring event. The sauropods would have been incorporated into the spiritual frameworks of every culture that lived alongside them, in the same way that elephants and lions and great whales have been incorporated into the spiritual frameworks of the cultures that lived alongside them. They would have been gods, or the mounts of gods, or the ancestors of gods, or the enemies of gods, or the guardians of sacred places. They would have been deeply embedded in the symbolic systems through which human beings make sense of the world. And in the modern world of our thought experiment, where those traditional communities still exist but now coexist with industrial civilization, the sauropod would occupy the same complex space that large charismatic megafauna occupy in our own world. Simultaneously a tourist attraction and an ecological nuisance. Simultaneously a symbol of national identity and a practical problem for farmers. Simultaneously a subject of scientific fascination and a target of political argument about land use and conservation and the rights of local communities. The arguments would be familiar. They would have the same structure as the arguments we already have about elephants and tigers and wolves. But the scale of the animal would make them more intense, the stakes higher, the trade-offs sharper. What would the science of studying a living sauropod look like? This is a question that captivates me, because the tools we would bring to understanding these animals are so much more powerful than what we have for reconstructing them from fossils. Paleontology, as extraordinary a science as it is fundamentally limited by what survives. Bone survives, teeth survive. Occasionally, skin impressions or gastric contents or traces of pigment survive. But soft tissue, behavior, physiology, the actual living mechanisms of an animal, these must be inferred from the preserved hard parts, using analogy with living animals and the principles of biomechanics and evolutionary biology. We're extraordinarily good at this kind of inference. The modern science of paleontology is far more sophisticated than even a generation ago. But there are limits. A living sauropod removes those limits. You can draw blood and analyze its composition, its oxygen-carrying capacity, its clotting factors, the specific proteins that reflect the animal's evolutionary history. You can implant a heart rate monitor and measure the cardiovascular dynamics directly, resolving the decades-long debate about how sauropod blood pressure functioned. You can attach accelerometers to the limbs and measure gait mechanics with a precision that no trackway analysis can approach. You can take tissue samples and sequence the genome, reading the evolutionary history of the lineage directly from its DNA. You can put a radio collar on a juvenile and follow it for its entire life, documenting growth rates, feeding patterns, social interactions, habitat preferences, and reproductive behavior with a completeness that transforms the science. The genome of a living sauropod would be one of the most scientifically valuable things in the world. Sauropods are archosaurs, and they share common ancestry with both birds and crocodilians, the two living archosaur lineages. Comparing the sauropod genome with those of birds and crocodilians would illuminate the specific genetic changes that underlie the sauropod body plan. The gene variants responsible for the extreme body size, the pneumatized bones, the long neck, the specific metabolic adaptations, the reproductive biology. It would allow us to date the evolutionary divergences between lineages with a precision that the fossil record alone cannot provide. It would reveal the molecular mechanisms of growth processes that produce animals of this size, which in turn might have implications for our understanding of the cellular mechanisms of body size determination in general, including in ourselves. Medical science would find it extraordinary. The sauropod's anti-cancer adaptations, because any animal that lives for decades and grows as large as a sauropod must have extremely robust mechanisms for suppressing the abnormal cell division that leads to cancer, would be a subject of intense biomedical research. The relationship between body size and lifespan in sauropods, a living animal of this size might live for 100 years or more, would illuminate fundamental questions in aging biology. The behavior of living sauropods, observed directly and continuously for the first time, rather than inferred from ancient bones, would overturn many current assumptions and confirm others. The social structure. Whether the animals form stable long-term bonds as elephants do, or loose aggregations as wildebeest do, or something with no modern analogue at all. The parental investment, if any. Do sauropods in our thought experiments still leave their eggs entirely unattended, as the fossil evidence from the Cretaceous suggests? Or has 66 million years of further evolution produced some degree of parental behavior, as we see in some modern birds and crocodilians? The communication system. What calls do they make? At what frequencies, and what do those calls mean? Do they have anything analogous to the complex vocal repertoires of elephants or cetaceans? Do they use infrasound for long-distance communication the way elephants do? And if so, what information do those signals carry, and how far do they travel? The feeding behavior would be among the most intensively studied aspects of living sauropod ecology. High-definition camera traps positioned in their feeding areas. GPS tracking of individual animals to document their movement patterns and food patch selection. Chemical analysis of the plants they choose and the plants they avoid, and of the specific ways their digestive chemistry processes different food types. The specific heights at which they browse in different seasons. The specific plant species they prefer in different parts of their range. the way they interact with trees whose top branches they can access, and the way that browsing pressure shapes the tree's response over years and decades. The browsing ecology of a living sauropod would be a discipline in itself, with implications for our understanding of the evolution of plant defenses, the coevolution of plants and large herbivores, and the way in which the feeding activities of a single species can restructure an entire plant community. The thermal biology would be another major research focus. The question of whether the large dinosaurs were ecto or endothermic, whether they generated their own body heat as mammals and birds do, or relied primarily on environmental heat as modern reptiles do, has been one of the most contested debates in paleontology for 50 years. If you like the video so far, please leave us a like and a sub. A sub to the channel helps us make more videos for you to watch and keep the channel alive. The consensus today, based on bone histology and isotope analysis and biomechanical modeling, leans toward a view in which the large dinosaurs occupied a middle ground, not as fully endothermic as a mammal or bird, but not as dependent on external heat as a modern crocodile. Very large body size itself provides thermal inertia, the tendency of a large mass to resist temperature change, and an animal the size of a sauropod might maintain a relatively stable and elevated body temperature simply by virtue of its mass, without needing to burn as much metabolic fuel per kilogram as a small mammal does to stay warm. But the specifics of this gigantothermy, as some researchers have called it, remain uncertain. A living sauropod would resolve that uncertainty immediately. You measure the body temperature directly. You implant a temperature logger and follow the animal through the seasons, through changes in weather, through periods of activity and rest. You compare its body temperature to ambient air temperature and to the temperature of the large mammals and reptiles living in the same environment. You take blood samples and measure the oxygen consumption of the tissues, which reflects the metabolic rate directly. Within a few years of having access to a living sauropod, the debate about dinosaur thermoregulation would be settled, not just for sauropods, but with implications for all the extinct dinosaur lineages, because the physiological mechanisms that large sauropods used would illuminate the ancestral state from which all the dinosaur lineages derived their thermal biology. The reproductive biology would take longer to study, because sauropods, if they have lifespans of decades and reach sexual maturity only after many years of growth, would not provide data on reproduction quickly. But long-term field studies, of the kind we conduct with elephants and great whales and great apes, would eventually document the full reproductive cycle, from mate selection to egg laying to hatching to the early growth period, the nest site selection, the clutch size and egg characteristics, the incubation period and the conditions required for successful development, the behavior of the hatchlings and the factors that determine early survival, the growth trajectory from hatchling to juvenile to subadult to adult, and the changes in diet and behavior and social relationships that accompany each stage. All of this would be scientific material of extraordinary value, not just for understanding sauropods specifically, but for understanding the evolution of reproductive strategies in large, long-lived animals generally. And here is something that would only become apparent over the very long term, over the decades of dedicated study that organizations like the long-running elephant research projects in Amboseli and elsewhere have modeled for large animal science. The individual recognition of sauropods, the documentation of individual variation in behavior, in habitat preference, in social relationships, in reproductive success, the discovery that individual sauropods have personalities, as individuals of every well-studied animal species eventually turn out to have, that some individuals are bolder or more cautious, more sociable or more solitary, more successful at finding food or at protecting their young. The recognition that what we call a species is not a uniform thing, but a collection of individuals, each with its own history and its own relationships, and its own particular way of navigating the world. The sauropods, once we had the chance to know them as individuals rather than as fossils, or as archetypes, would reveal the same irreducible complexity of individual life that every thoroughly studied animal species reveals. Let us now think about the geography of this world more specifically. Where in the modern world would the large sauropod populations be most likely to persist? The southern hemisphere is the obvious starting point. South America, Africa, and the Indian subcontinent are the regions where the Titanosaur lineages were most diverse and numerous in the late Cretaceous. And in our alternate world, the continuation of those lineages into the present would most naturally be concentrated in the same general regions. South America, with its vast interior grasslands and gallery forests, its enormous river systems, its relatively low human population density in much of the interior, would be the most likely heartland of the global sauropod fauna. The Amazon basin, the Cerrado, the Gran Chaco, the Pantanal, these diverse and extensive ecosystems would provide the kind of resource base that could sustain populations of very large herbivores, though the specific habitats favored by sauropods might be different from what we might naively expect. Because the sauropod-adapted ecosystems of 66 million years of continuous evolution would themselves be different from the mammal-adapted ecosystems we know today, Africa would be another major stronghold. The continent's geographic stability over the past 66 million years, its relative lack of the dramatic tectonic upheavals and climate extremes that have characterized some other regions, and its long continuity of diverse megafauna would make it a hospitable environment for sauropod persistence. The broad savannas and bushveld of eastern and southern Africa, the forests of Central Africa, the Sahel grasslands, all of these would potentially support sauropod populations of varying sizes and ecological roles. The African sauropods of our thought experiment would have evolved alongside the African hominin lineages, including the ancestors of modern humans, for millions of years, creating a relationship between proto-humans and these enormous animals that would be one of the most fascinating topics in the alternative world paleoanthropology. Did early hominins scavenge from sauropod carcasses? Did they develop hunting strategies for the hatchlings or juveniles? Did they compete with sauropods for water sources? Did the presence of sauropods in the African landscape influence the evolution of human cognitive and social capacities in ways that we can only speculate about? The Indian subcontinent, which was an island for much of the Mesozoic and early Cenozoic before colliding with Asia around 50 million years ago, would have carried its own lineage of sauropods through that collision and into the merged Asian landmass, potentially mixing with the sauropod fauna of Asia proper and creating a rich zone of hybridization and evolutionary novelty in the collision zone that is now South Asia. South and Southeast Asia, with their diverse tropical and subtropical habitats, would likely support sauropod populations through the Cenozoic. Though the specific evolutionary history of Asian sauropods in this alternate timeline is harder to predict, given the complexity of the Asian biogeographic history. Northern Asia, Europe, and North America are harder cases. These regions experienced the most dramatic climatic fluctuations of the Cenozoic, particularly during the Pleistocene glaciations, when ice sheets covered enormous areas and the habitats suitable for large herbivores were compressed into much smaller refugia. In our own world, many of the large mammals of these regions survived the Pleistocene glaciations, but went extinct at the end of them, possibly due to a combination of climate change and the arrival of modern humans with sophisticated hunting technologies. In a world with living sauropods, the Pleistocene glaciations would have been an enormous test of the sauropod lineages in the northern continents. The cold-adapted sauropod populations would have needed to either migrate southward during glacial maxima, tracking the retreating habitats, or develop physiological adaptations to cold that would have been without precedent in the sauropod evolutionary history. Some lineages would have survived this test, and some would not. The Northern Hemisphere sauropod fauna in our thought experiment would likely be less diverse and less numerous than the Southern Hemisphere fauna, a reflection of the greater climatic stress the northern lineages have faced. In North America, where sauropods were present through much of the Jurassic and Cretaceous, The alternate history fauna would depend on how well the North American lineages survived the Pleistocene. Titanosaur diversity in the late Cretaceous of North America was somewhat lower than in South America, and the North American lineages might have been more vulnerable to the climatic extremes of the Cenozoic. But even reduced populations of sauropods in the interior grasslands of North America, in the river valleys and forests of the southeast, in the warm coastal zones along the Gulf of Mexico and the Pacific, would be a defining feature of the North American landscape in any alternate timeline where the extinction did not occur. Now, let us think about a specific moment. Not a mythological moment or an abstract ecological scenario, but a specific, grounded, sensory moment of encounter between a human being and the largest dinosaur alive today. You are a field biologist. You work for a government research institute in what is called the Alto Paraná region of interior Brazil, in the sauropod conservation corridor that covers 3 million hectares of cerrado and gallery forest along the upper Paraná River. You have been working here for 6 years. You have seen many sauropods. You have collected hundreds of hours of video footage. You have taken tissue samples from tranquilized juveniles. You have fitted GPS collars on subadults. You are not easily startled by them. You have learned the way every field worker learns to read their behavior, to understand the signals that indicate agitation, the slow lateral swaying of the enormous tail, the lowering of the neck from its normal horizontal carriage to a position angled slightly downward, the subtle change in the rhythm of the footfalls that suggests the animal is thinking about moving away from something it has noticed. But this morning is different, because the animal you are watching is not the 40-ton females of the Itaipu herd that you usually work with, or the subadults you have been following since they left their birth herd 3 years ago. This morning, at first light, while the mist is still sitting in the low places along the river and the cerrado birds have just started their dawn chorus, the big male has come into the open meadow below the observation platform. The biggest male in the corridor. The one the team calls Goliath, not because it is a particularly subtle name, but because there was no other name that seemed adequate. Goliath has been GPS tracked for 4 years, but he is rarely seen in the open. He spends most of his time in the tall Cerradão forest, the dense woodland on the slightly wetter ground near the river, where his dark coloration, greys and deep muted greens that shift with the light, makes him surprisingly difficult to see against the dappled background of large trees and lianas and the lateral columns of sunlight breaking through the canopy. But now he is in the open. And in the open, without the visual compression of the forest to distort your perception, you can see him whole for the first time in the 4 years you have been tracking him. The GPS data told you he was large, that his daily movement ranges were larger than any other individual in the corridor, that he spent more time than any other tracked animal in the areas of tallest trees, which you had assumed was a dietary preference for the high canopy browse those areas provided. Now, in the open, you understand the other reason. He has to be in the tall forest, because in shorter vegetation his neck, when extended, simply extends above the treetops. He is moving slowly along the edge of the meadow, the massive head and long neck carried in the characteristic horizontal position, swinging gently as he walks the way a pendulum swings. Not rapidly, but with an unhurried deliberateness that you have come to think of as the fundamental rhythm of a very large life. Each footfall compresses the wet morning grass into the soft, dark soil with a sound that you feel in your feet on the platform before you hear it in your ears. The tail, a dozen meters of tapering muscle and bone, sweeps slowly behind him, the tip at about knee height, leaving a shallow furrow in the wet grass where it drags. His breath in the cool morning air comes as visible puffs of vapor at intervals of maybe 15 or 20 seconds. The slow respiratory cycle of an animal whose lungs, you know from the literature on estimated lung capacity in titanosaurs of his size, hold something like 1,500 liters of air. He stops. You are perhaps 300 meters away on the platform, and you are not downwind, but he has noticed something. A change in the quality of the light, perhaps, or a sound too low for you to hear. A signal from another animal across the river. His neck swings slightly, the head tilting to orient one eye toward a particular direction, with the sideways-looking gaze that large sauropods use when they are attending to something. The way a bird tilts its head to listen. He holds this posture for a long time, long enough for you to realize you have not moved, that you have been holding your breath slightly, though you are in no danger at this distance, and Goliath has seen human beings and observation platforms before and regards them with a calm disregard that might be mistaken for tolerance, but is almost certainly something simpler. A calibrated assessment that the thing on the platform is small and does not smell like a threat. Then he moves again, turns slightly toward the river. The neck dips, and the great head moves downward in a long, slow arc, and for a moment he is drinking, the muscular throat working in the slow, rhythmic contractions of an animal, moving large volumes of water upward against gravity, and you are doing the rapid mental arithmetic you always do when you watch this, estimating the column of water in the neck, the cardiovascular work required, the rate at which the head must be lowered to prevent the blood pressure at the brain from spiking to dangerous levels, wondering again whether the jugular vein of an animal this large has some valve system, some mechanism we have not yet been able to document, that prevents the blood from simply rushing headlong to the brain under the force of gravity every time the neck is lowered. And then he lifts his head again, and the neck swings back to its horizontal carriage, and he begins to walk back toward the forest, and in a few minutes, he is in the shadow of the tall trees. And then he is the shadow of the tall trees, and then he is invisible, and all that is left is the slow fading of the ground vibration, and the trampled path through the wet grass, and the deep round impressions of his feet, slowly filling with water from below. You sit in the quiet for a long time afterward. You have seen him before, you will see him again. But every time, there is something that the data and the GPS tracks and the tissue samples and the conference papers cannot capture. And that is the simple, overwhelming, irreducible fact of an animal that large being alive in the world. Being real. Being here in the morning mist. Breathing visible breath. Drinking from the river you can see from the platform. Casting a shadow that moves across the meadow with all the unhurried gravity of a cloud. There is something that the human nervous system does in the presence of an animal that large. Something that is not fear exactly. Though it is related to fear, and not awe exactly. Though it is related to awe. It is more like a recalibration. A moment in which your ordinary sense of your own scale in the world, the scale at which human beings habitually operate, is temporarily suspended and replaced by an awareness of a much larger scale. A scale at which you are very small and the world is very big, and the animal moving through the mist is something that the world has been carrying for a very long time. That recalibration is something human beings have not had the opportunity to experience in a very long time in our actual world. We have elephants and whales, and they are genuinely large, genuinely impressive, genuinely capable of producing that moment of scale adjustment when you encounter them close up for the first time. But even the largest elephant, the largest blue whale, does not produce quite the same effect as what the encounter with an animal 10 or 12 times an elephant's mass would produce. The paleontologist Paul Sereno, one of the researchers most intimately associated with the discovery and description of enormous theropod and sauropod dinosaurs in Africa, has written about the experience of working in the presence of sauropod bones, not living animals, just the fossilized remains, and finding that even the bones produce a version of that recalibration. A single femur, the thigh bone, of a large titanosaur is taller than most human beings and weighs, in its original biological form, before mineralization, hundreds of kilograms. You stand next to it and you understand, in a way that photographs and diagrams do not communicate, that the bone itself is larger than you are. And the bone is just the support structure for an animal that was far larger than the bone. We have lost something in our world without the great dinosaurs. Not a practical thing, not a thing that impoverishes us in any material sense, but something in the phenomenological register, in the domain of experience. We have lost the daily possibility of encountering an animal so large that it makes you aware of your own smallness in a way that changes something in your perception, however briefly. The blue whale comes close, but we rarely encounter blue whales in the wild. And when we do, it is almost always from a boat, at the surface, where we see the back and the blowhole and perhaps the tail, not the full three-dimensional presence of the animal. To see a blue whale fully, you would need to be in the water alongside it, and in the water alongside a 25-meter, 150-ton animal, most people are too frightened to attend to anything beyond their own survival instincts. But a large sauropod, moving through a landscape on land, visible from a distance, visible whole, is an experience that would be available in a way that the great whales are not. You could watch it for hours. You could observe it in the context of its actual ecological role, feeding and moving and interacting with its environment in ways that revealed the full texture of its life. You could understand it, over time, as a participant in an ecosystem, rather than as an overwhelming presence in a void. And that understanding, that sustained encounter with something genuinely vast and genuinely alive, would be, for any human being capable of attending to it, among the most profound experiences available in the natural world. The conservation of living sauropods in our thought experiment would be one of the great political and ethical challenges of the age. Not because the arguments about their value would be difficult to make. An animal this large and this ecologically significant is its own argument for preservation, but because the scale of the resources required to preserve them would be enormous. Protected areas large enough to sustain viable sauropod populations would need to be hundreds of thousands of hectares in size, in regions where land has enormous agricultural or mineral value, and where the human communities living in and around the protected areas have legitimate needs and rights that cannot simply be overridden in the name of conservation. The political economy of sauropod conservation would be a permanent, difficult, and occasionally bitter argument between the interests of local communities, national governments, the international conservation community, and the scientific establishment. It would be fought in legislatures and in international treaty negotiations, and in the courts. It would be won and lost in different places at different times, with populations expanding in areas of strong governance and shrinking in areas of weak governance or intense land pressure. And there would be poaching. There is always poaching. Wherever large and valuable animals exist in the world today, there are human beings willing to kill them for money. Rhinoceros horn, elephant ivory, tiger bone. The economic incentives for killing large animals are powerful and persistent. And the enforcement of wildlife protection laws is always imperfect and often corrupt. What parts of a sauropod would command high prices on illegal markets? The bones, certainly, which in a world where sauropods are the megafauna rather than the fossil record would be available in enormous quantities, and would have whatever cultural and material value traditional societies attributed to them over tens of thousands of years of coexistence. The eggs, which are large and presumably require significant incubation resources, would be valuable in markets that prize exotic animal products. And perhaps the animals themselves, alive, the ultimate status symbol for the kind of wealthy collector who, in our world, pays fortunes for rare exotic animals. The illegal trade in live sauropod juveniles would be a law enforcement challenge unlike anything in modern wildlife crime, given the logistical difficulties of actually smuggling a young dinosaur across international borders. But the history of the illegal wildlife trade suggests that where there is sufficient financial incentive, the logistics are eventually solved. The legal tourism economy around living sauropods would be one of the largest wildlife tourism industries in the world, surpassing the safari industry of Africa, the whale watching industry, and anything the wildlife tourism sector currently contains. The combination of extreme size, relative accessibility in open landscapes, and the deep human fascination with dinosaurs that our own culture demonstrates so consistently would create a demand for sauropod viewing experiences unlike anything before it. The Serengeti draws perhaps 1 million visitors per year. A sauropod reserve of comparable size and accessibility would likely draw many times that number, and those economic incentives would be among the most powerful forces for the animal's protection. Imagine the range of human encounters this tourism would involve. The wealthy traveler in a specially designed viewing vehicle, armored and elevated, approaching a feeding group of females and juveniles in the Corrado at midday. If you like the video so far, please leave us a like and a sub. A sub to the channel helps us make more videos for you to watch and keep the channel alive. The researcher on the observation platform in the early morning, watching the big male drink from the river. The ranger in the buffer zone community, navigating the daily negotiation between the Sauropod Corridor Management Authority and the farmers whose maize fields border the protected area. The child in a primary school in a nearby town, going on a class trip to the viewing area for the first time, standing at the fence with her class and looking up at an animal that is real, that is moving, that is eating the leaves of a tree 30 meters away with a placid efficiency that somehow makes the scale of it more, not less, overwhelming. The indigenous elder in the community whose traditional territory overlaps with the sauropod corridor, who knows the animals by individual recognition, who knows which valleys they favor in which seasons, whose community has managed the relationship with these animals through cultural practices developed over many generations, and who finds the arrival of the International Conservation Establishment with its GPS collars and blood samples and camera traps to be a complicated thing, simultaneously welcome and intrusive, a validation of the animal's importance, and an imposition of an outside framework on a relationship that was working before the scientists arrived. All of these encounters, all of these human relationships with the living sauropod, would together constitute the cultural dimension of a world that contains these animals. And that cultural dimension would be vast and various, and would change over time, and would mean different things to different people. But at its core, in the way that the core of any culture's relationship to its most significant wildlife always comes back to something fundamental about what it means to share the world with other living things, it would mean this: that there is something on this earth larger than human ambition, and older than human civilization, and more ancient than human memory, and that its continued existence is a reminder that the world was not made for us alone, and that we are participants in a story much larger and much longer than our own. Think about what the fossil record would look like in this alternate world. Think about the paleontologists who, in this alternate timeline, are studying the Mesozoic history of life. They still find fossils. The Jurassic and early Cretaceous sauropods still left their bones in the rock, and those bones are still there, waiting to be found. But the paleontologists studying those ancient animals have something that our own paleontologists do not have, and that is a living reference point. They know what a sauropod metabolic rate looks like, because they can measure it in living animals. They know what sauropod bone histology corresponds to in terms of growth rate, because they can compare it to the bone histology of living animals whose growth rates are directly documented. They know what a functional sauropod cardiovascular system looks like, because the large living titanosaurs have cardiovascular systems that have been thoroughly studied. They can use all of this knowledge to work backward, to interpret the Mesozoic fossil evidence with a precision and confidence that our own paleontologists, working entirely from analogy with the mammals and modern reptiles and birds, cannot achieve. The study of fossil sauropods in this world would be richer and more grounded than our own paleontology of the group, but it would also have a different emotional texture. When you study an extinct animal, there is an elegiac quality to the work. You are reconstructing something that no longer exists, recovering something from absence. When you study the ancestors of a living animal, the work feels more continuous, more connected to the present. The Jurassic sauropods are not gone. They are behind. They are the past of something that is still here. The bones in the rock are the history of Goliath, who was drinking from the river this morning, whose GPS track shows that he has moved 3 kilometers since dawn and is now in the forest near the second observation station. Paleontology in this world is not the recovery of the lost. It is the reading of a lineage that still has a present and possibly a future. And the future. What does the future of a world with living sauropods look like? On the timescale not of human lifetimes, but of geological time. We are in the Anthropocene, the age in which human activity is the dominant force shaping the Earth's climate, ecosystems, and biodiversity. The changes we are driving, rising global temperatures, sea level rise, ocean acidification, habitat destruction, species extinction, are happening faster than the evolutionary processes that might allow species to adapt to them. Large animals with long generation times are especially vulnerable, because they cannot evolve fast enough to track the rapidly changing environment. Elephants are already stressed by climate change in parts of their range. Polar bears face an existential crisis as the Arctic sea ice on which they depend shrinks. The large baleen whales, which survived millions of years of natural climate variability, are now challenged by the pace and scale of the human-driven changes to the ocean chemistry and temperature. Sauropods, with their presumably very long generation times and enormous resource requirements, would be among the most vulnerable of all animals to the kind of rapid environmental change the Anthropocene is producing. A species that takes perhaps 20 years to reach reproductive maturity, and that produces only a few clutches of eggs in a reproductive career of several decades, cannot adapt by natural selection to environmental changes that play out over decades. It can only survive them if the changes are not too severe for the physiological tolerances of the current adult population, and if the habitats they depend on remain available in sufficient extent. Climate change in our actual world is already driving shifts in the vegetation communities of the tropical and subtropical regions where sauropods would be most numerous. The Cerrado of Brazil is one of the most biodiverse ecosystems in the world, and one of the most threatened, with large areas converted to soy and beef production, and the remaining natural vegetation increasingly stressed by drought and fire. The savannas of Africa are changing as rainfall patterns shift and temperatures rise. The gallery forests along tropical rivers, which would be among the most important sauropod habitats given those animals' need for water, are among the most vulnerable to the combination of deforestation and climate-driven hydrological change. In a world with living sauropods, the conservation community would face the challenge of protecting not just the animals, but the entire ecosystem architecture that sustains them, on a planet whose environmental future is increasingly uncertain. The protected areas would need to be not just large, but strategically positioned to allow animal movement across the landscape as conditions change. The connectivity corridors that allow individual animals to move between protected areas, tracking the shifting distributions of food and water, would be among the most critical elements of the conservation infrastructure. The management of those corridors in a landscape increasingly dominated by human land use would require a level of international cooperation and political commitment that the wildlife conservation community has been struggling to achieve for decades. And yet, and this is perhaps the most important thing to say about the future of living sauropods in the Anthropocene, the presence of these animals would itself change the politics. The presence of animals this large and this charismatic in the world changes what is imaginable in terms of the scale of conservation effort. It changes what is politically possible. It changes the emotional valence of the arguments about land use and climate and biodiversity. We have trouble in our world mobilizing sufficient political will to protect the endangered species we have, partly because many of those species are small and obscure and difficult to see, and not particularly easy for most people to care about in a visceral way. We protect charismatic megafauna more effectively than we protect the invertebrates and fungi and plants that do much of the ecological work in the world, because people can see the megafauna and feel something about them. A living sauropod, 70 tons of evolutionary history walking through a morning mist, its breath visible in the cool air, its footfalls felt in the soles of your feet, would be the most charismatic megafauna on the planet by a vast margin. None of this means the sauropods would be safe. No large animal is safe in the Anthropocene, and the combination of habitat loss and climate change, and the relentless pressure of a growing human population on the land and water that large animals need, would threaten sauropod populations as surely as they threaten elephant and rhinoceros and great whale populations in our own world. The threat would be real. The losses would be real. Some populations would go extinct in some regions, but the overall story, in a world that had the good fortune to retain these animals through the Cenozoic and into the modern era, would be a story of extraordinary richness. A world more alive with wonder than our own. A world in which the baseline for what is possible in the domain of animal life is set at a height that makes everything else more vivid by comparison. Let us return one more time to the meadow at dawn. The mist is lifting now. The Corrado birds are in full morning voice, a brilliant, complex, layered chorus of species that evolved over millions of years in a landscape shaped partly by the activities of the animals whose presence you are still feeling as a residual vibration in the platform beneath your feet. The GPS tracker shows Goliath moving deeper into the forest, heading north along the river valley toward the area of tall pterodon that he uses during the middle of the day, where the canopy is dense enough to provide shade and the understory is open enough for him to move through without constant contact with the vegetation on his sides. You will not see him again until late afternoon, if then. But he is there. From 4 years of data and from this morning's half hour of direct observation, that he is there, that he will be there tomorrow, that barring accident or disease or the kind of catastrophic breakdown in conservation governance that you work every day to prevent, he will be there for decades more. That he has a range he knows intimately, rivers and valleys and particular trees whose browse he returns to season after season. That he is part of a population of animals whose collective presence has shaped this landscape for far longer than any human community has lived in it. That the trampled paths through the Corrado grasses, the deep round depressions at the river's edge, the trees in the forest whose lower branches have been stripped year after year to a height of 15 meters, while their upper canopy still grows freely above the reach of even the tallest neck. All of these are the signatures of a life lived at a scale you can study and track and measure, but cannot fully comprehend. Because comprehension, real comprehension, the kind that lives in your body rather than in your data, requires a matching of scales that you, as a human being, will never quite achieve. You are too small. You live too briefly. You will never be inside the world that Goliath inhabits, only adjacent to it, only watching from the platform while the great animal moves through the mist below. And that is not a failure. That is simply the condition. Every scientist who works with an animal very different from themselves, every researcher who spends years in the company of elephants or whales or great apes, eventually arrives at the same acknowledgement. You can know an enormous amount about an animal, you can document its behavior and its physiology and its genetics and its ecology to a degree of precision that would have been unimaginable a generation ago, and still find that the animal remains, at some level, other. Genuinely, irreducibly other. Living in a world that is adjacent to yours but not identical to it. Experiencing the same landscape through senses and a body and a temporal frame so different from your own that full translation is impossible. The otherness of the very large animal is one of the most interesting versions of this experience, because size itself is a kind of fundamental difference, a difference in the basic parameters within which a life is lived. Goliath, in this morning, has already covered a distance that would take you an hour to walk. He has consumed, in his browsing, plant material that weighs more than you do. He has been alive for, let us say, 60 years, which means he has seen this valley through drought years and flood years, and the slow creeping changes of a warming climate, has known this river when it ran higher and when it ran lower, has found his way through every season with the accumulated knowledge of 6 decades of living in this place. He will likely outlive you. His descendants, if he has been reproductively successful, which the GPS data suggests he has been, will be in this valley long after both of you are gone. The lineage he carries, the Titanosaur lineage that has been walking the landscapes of the southern continents since before the asteroid that, in our actual world, ended everything, has been here for so long that the human story is, by comparison, a brief and recent thing. A paragraph at the end of a very long book. That is the thought to carry into sleep. Not the science, though the science is wonderful. Not the conservation politics, though they matter enormously. Not even the direct experience of the encounter, though that is extraordinary. But the deep time of it. The 66 million years that, in this alternate world, did not end in fire and cold and darkness, but continued, season after season, generation after generation, the sauropod lineage finding its way through every challenge the Cenozoic threw at it, adapting and persisting and remaining, somehow, stubbornly, magnificently present, while the continents drifted, while the climate cycled through warm periods and ice ages and warm periods again, while the grasslands spread and the forests contracted, and the grasslands contracted and the forests spread, while the mammals evolved and diversified and produced, eventually, the small-brained, large-tongued, endlessly curious primate that is now sitting in a field station in the Corrado at dawn, watching a GPS track move slowly through a forest, writing notes about an animal that weighs more than the field station and all of its equipment combined. 66 million years. Think about how long that is. The asteroid struck 66 million years ago. If you compress the age of the universe into a single calendar year, the asteroid impact would have happened around the 23rd of December. And since then, in this imagined world, not just silence and empty rock, but continuous life at the largest scale the terrestrial world can sustain. Continuous breath and movement, and feeding and reproduction. Continuous ground vibration, and deep vocal resonance, and the slow patient work of enormous feet reshaping the landscapes they move through. 66 million years of that. 66 million years of the largest animal that ever walked on land, still walking on land. 66 million years of the world being required to accommodate something that vast. It is a thought that puts things in their proper proportion. A thought that makes the small anxieties of a human life feel, for a moment, appropriately small, not meaningless. The small things are not meaningless, but small, properly small, in the context of a world that has been carrying this much weight for this long, and that carries it still somewhere in the imagined valley beyond the observation platform, where the GPS tracker is moving north through the tall trees, and the morning is golden and the ground remembers every footfall of the animal that has just passed through it. Rest now. Let the great animals walk through the world you have built for them tonight. Let the ground vibrate beneath your bed, the way it would vibrate if something truly enormous were moving through the dark outside your window. Unhurried and ancient, and completely indifferent to the smallness of the hour. Let the long neck swing through the mist. Let the tail sweep slowly through the wet grass. Let the breath come in long, visible plumes in the cool morning air. The slow, deep respiratory rhythm of something that was here long before cities. Long before language, long before the first tentative ancestor of yours stood upright on a savanna somewhere in East Africa, and looked out across a landscape that was already, even then, shaped by animals larger than anything you will ever see in the world, as it actually is. They are gone. There is one more dimension of the living sauropod that we have not yet examined carefully, and it is perhaps the most intimate one: the mind, the brain, the question of what it is like, internally, to be an animal this large. This is a question that verges on the philosophical, because we have no direct access to the subjective experience of any animal other than ourselves. And the honest scientific position is that we cannot know what it is like to be a sauropod any more than we can know, in Thomas Nagel's famous formulation, what it is like to be a bat. But we can make some inferences about the cognitive architecture of these animals, and those inferences are interesting in their own right. The brain of a sauropod was, relative to its body mass, very small. This is a consistent finding across the sauropod group, confirmed by endocasts, the casts of the interior of the skull that preserve the rough shape and size of the brain. A large titanosaur would have had a brain weighing perhaps a few hundred grams, set inside a skull that might weigh several hundred kilograms, and attached to a body weighing 70 tons. The encephalization quotient, the ratio of actual brain mass to the brain mass expected for a mammal of the same body weight, would be extremely low by mammalian standards. The popular image of dinosaurs as dim-witted creatures is largely a myth for the theropod lineages, particularly the Maniraptorans, which had relatively large brains and demonstrated complex behaviors. But for sauropods, the brain-to-body ratio is genuinely low, and the neural architecture appears to have been organized primarily around the sensory and motor functions that manage a very large body, rather than around the kinds of cognitive flexibility and social intelligence that characterize the large-brained mammals. This does not mean sauropods were mindless. A living animal with a functioning nervous system is always more than the sum of its neural measurements. The ability to navigate a complex landscape, to remember the locations of food and water sources across a range of hundreds of square kilometers, to recognize other individuals in a social group, to respond appropriately to predation threats and to the reproductive signals of potential mates, requires a degree of behavioral sophistication that should not be dismissed simply because the brain that produces it is smaller relative to body size than a mammal's brain would be. The intelligence of an animal is not solely a function of the size of its brain. It is a function of the specific architecture of that brain, the particular computations it performs efficiently, and the behavioral demands of the ecological niche the animal occupies. What cognitive demands does a large sauropod's ecological niche actually place on it? The navigation demands are significant. An animal that ranges over hundreds of square kilometers must have a detailed spatial memory of its environment, must be able to locate water sources and food patches and resting sites and nesting areas without visible landmarks over distances of many kilometers. Modern elephants, who face similar navigation demands over similar or even larger ranges, have demonstrated remarkable spatial memory in experimental and observational studies, remembering the locations of water sources and food patches across ranges of thousands of square kilometers and over time periods of decades. There is no particular reason why sauropods should not have similar spatial memory capacities, given the similar ecological demands. The social demands are less clear and more interesting. The fossil evidence from trackways suggests that sauropods sometimes moved in groups, and the evidence from nesting sites suggests colonial nesting with many individuals using the same site simultaneously. But whether these aggregations involve the kind of long-term stable social relationships that characterize elephant herds, or the more fluid and temporary associations of large ungulates like wildebeest or caribou, is something we cannot determine from the fossil record alone. In the living sauropod of our thought experiment, this question would be directly accessible. Does Goliath know the females of the Itaipu herd as individuals? Does he have preferred associates among the males of the corridor, individuals he tolerates at close range more readily than others? Does he maintain a mental model of the social structure of the population that allows him to predict the behavior of other individuals he encounters? These are the kinds of questions that long-term behavioral studies eventually answer, and the answers tend to be more nuanced and more interesting than the initial assumptions. The temporal perception of a very long-lived animal is another fascinating question. A sauropod that lives for a century experiences the world at a different temporal scale than a mouse that lives for 2 years or a human being that lives for 80. The long-lived animal accumulates knowledge of its environment across timescales that encompass multi-year drought cycles, multi-decade changes in vegetation, the lives and deaths of individual trees that a shorter-lived animal would never see from seed to senescence. Whether sauropods made use of this accumulated temporal knowledge in ways analogous to what we see in long-lived elephants and great apes, whether individual experience shaped their behavior in ecologically significant ways, is a question that gets at the very heart of what intelligence is for and what it is like to have it at different timescales. In a world where sauropods are living animals rather than fossils, the cognitive ethology of these animals would be one of the most active and contested fields in behavioral science. The initial assumption, based on the brain-body ratio, would be that sauropods are behaviorally simple animals, operating primarily on instinct and basic conditioning. If you like the video so far, please leave us a like and a sub. A sub to the channel helps us make more videos for you to watch and keep the channel alive. The actual observations, accumulated over years of field study, would likely be considerably more interesting than that initial assumption, just as the actual behavioral observations of every large animal that has been studied with sufficient patience have turned out to be more interesting than the initial assumptions. The history of behavioral science is partly a history of underestimating the cognitive complexity of animals that lack the specific neural architecture we recognize from our own experience. The vocalizations of sauropods, in a world where we can study them directly, would be an entire research program in themselves. We know that modern archosaurs, both crocodilians and birds, are vocal animals with complex communication systems. We know that the structure of the middle ear and the auditory nerve in sauropods, as reconstructed from fossils, suggests sensitivity to sound in the low frequency range. We can model the acoustic properties of the sauropod body, particularly the long neck and the large body cavity, and estimate what frequencies they would be efficient at producing and at receiving. But we cannot know, from fossils alone, the actual acoustic repertoire of a living sauropod. What calls do they make in what contexts? Do young animals make different calls than adults? Do females and males have different vocal repertoires? Do they have something analogous to individual signature calls, the way dolphins have signature whistles that allow individuals to identify themselves? The acoustic ecology of a living sauropod population would be one of the most extraordinary sensory environments imaginable, especially if, as seems likely, the primary communication frequencies are in the infrasound range below the threshold of human hearing. You would be surrounded by a communication system you could not perceive without instruments. A deep conversation happening continuously in the substrate beneath your feet and in the air around you. Invisible and inaudible to your unaided senses, but real and rich and structured in ways that carry information between individuals across kilometers of landscape. The infrasound calls of large sauropods, if they produce them, would travel through the earth as well as through the air, because low-frequency vibrations couple efficiently between the air and the ground at their point of contact. An animal standing on the ground would receive these vibrations through its feet, through the contact between its body and the earth, as well as through its ears. The foot, as a sensory organ for detecting ground vibrations, is something we know is important in elephants, which have specialized mechanoreceptors in the soles of their feet that are sensitive to the seismic signals produced by other elephants calling at infrasonic frequencies. Sauropods, with their much larger feet in contact with the ground over a much larger area, might be exquisitely sensitive to ground-borne vibrations, able to detect the calls and footfalls of other sauropods at distances of many kilometers through the seismic channel alone. In this world, the soundscape of any sauropod habitat would be multidimensional in a way that human senses can only partially access. The audible component, the sounds we can hear, would include the deep percussion of footfalls, the low rumbling of digestive systems, the occasional audible vocalization in the lower ranges of our hearing. The inaudible component, the infrasound calls traveling through air and earth, would be a continuous and complex acoustic environment that the sauropods themselves navigate and communicate through, but that human observers can only access with instruments. To fully experience the acoustic world of a sauropod landscape, you would need a seismometer and an infrasound microphone and a spectrogram display, and even then, you would be receiving the data rather than experiencing it, because your body does not have the mechanoreceptors to feel what the sauropods are feeling as they stand on the ground that carries their communications. The metabolism of the living sauropod is something that would be intensively studied from the earliest days of scientific access to the animals. The question of how an animal this large maintains its energy balance, how it takes in enough food and processes it efficiently enough to fuel a body of this mass, is fundamental to understanding the animal's ecology and its place in the ecosystem. The metabolic rate of large animals scales with body mass, but not proportionally. Very large animals have lower mass-specific metabolic rates than small animals, meaning they consume less energy per kilogram of body weight. But because their total body mass is so enormous, their absolute energy requirements are still very large. A sauropod the size of Patagotitan, even with a mass-specific metabolic rate far lower than a mammal of comparable size, would need to process enormous quantities of food energy per day to maintain its body temperature, power its locomotion, and support the continuous growth of new tissue. The gut microbiology of a living sauropod would be one of the most immediately accessible aspects of its physiology. Fecal samples, abundant and collectible without any direct intervention with the animals, would provide material for microbiome analysis, revealing the specific microbial community responsible for fermenting and breaking down the plant material the sauropod consumes. That community would likely be unlike anything we have characterized in any living animal, a treasure trove of novel microbial species and enzymatic capabilities shaped by tens of millions of years of coevolution with an animal unlike any that has been studied before. The growth biology of sauropods would be one of the most immediately fascinating areas of research. We know from bone histology that sauropods grew extremely rapidly for large animals, with growth rates that in some juvenile specimens appear to have approached or even exceeded those of large mammals. The lines of arrested growth visible in fossil bones, analogous to tree rings, suggest seasonal variation in growth rate, with rapid growth in favorable seasons and slower growth or growth arrest in unfavorable ones. Understanding how a living system can orchestrate growth from a hatchling the size of a human infant to 70 tons without catastrophic failure, without the uncontrolled cell proliferation that we call cancer, without the mechanical failure of bones and joints under the increasing load, would be a profound contribution to biomedical science. The lifespan of a large sauropod would be one of the most eagerly anticipated pieces of data from long-term population monitoring. We have estimates from bone histology of the ages of specific fossil individuals, suggesting that some large sauropods lived for many decades, but the fossil record inevitably overrepresents the older age classes in populations, because larger, more mature individuals have more mineralized bones that preserve better. A living sauropod, fitted with a uniquely identifiable marker as a hatchling, and then followed throughout its life, would eventually provide a definitive answer. A lifespan of a century or more would put sauropods among the longest-lived vertebrates known, and would raise profound questions about the mechanisms of longevity in very large animals. All of this, the metabolism and the immune system and the growth biology and the cognitive ethology and the acoustic communication and the reproductive biology, all of it would be known, documented, argued over, and slowly understood in a world where the sauropods never went away, And all of it would feed back into our understanding of the broader history of life, illuminating not just the sauropods themselves, but the entire Archosaur lineage, the evolutionary trajectory that connects the earliest dinosaurs of the Triassic to the modern birds and to these massive animals still walking the landscapes of the southern hemisphere. We would know ourselves better in this world because we would have a richer picture of the evolutionary history that we are part of. A picture that includes not just the mammalian lineage that gave rise to us, but the great Archosaur radiation that has been the other dominant force in terrestrial vertebrate evolution for 250 million years. In our world, we have only fragments, bones in the rock, footprints in ancient stone, preserved skin and eggs, and the occasional miraculous specimen where something has been permineralized in such a way that we can see the outline of organs or the structure of skin that is normally lost to time. We reconstruct from these fragments with remarkable skill and with genuine insight, and the picture we assemble is detailed and rich and constantly improving as new specimens are found and new analytical techniques are developed. But it is still a reconstruction from fragments, still a painting made from very few colors, still a story read through many gaps and much uncertainty. In the alternate world we have been exploring tonight, those gaps are filled. The uncertainty is resolved, not all of it, not immediately, but steadily, across decades of direct observation and measurement and analysis. The living animals answer questions that we have been arguing about for 150 years of paleontology. They raise new questions in their place, as living things always do. Questions that no fossil could ever pose because fossils do not behave, do not communicate, do not get sick or grow or reproduce or die in ways that can be observed and documented and understood. The living sauropod is infinitely more informative than the best fossil sauropod ever could be. Because it is living. Because it is doing all the things that life does, and those things leave traces not only in rock, but in the continuing fabric of the world, in the ecosystems they shape and the genomes they carry, and the cultural memories of the communities that have lived alongside them, and the scientific records of the researchers who have devoted their lives to understanding them. This is what we have lost. This is what the asteroid took from us 66 million years ago, on a day that we can reconstruct but will never know, that began like any other day in the late Cretaceous, and ended with the sky on fire, and the darkness falling, and the great animals dying, not all at once but slowly, over months and years, as the ecosystem they depended on collapsed layer by layer around them. The sauropods were already declining in diversity by the end of the Cretaceous. The classic lineages of the Jurassic were gone, but the titanosaurs were still there, on the southern continents, still diverse, still large, still walking, and then they were not. The bones remain. In the Badlands of Patagonia, in the red rock formations of the New Ken, the bones of Patagotitan and Dreadnoughtus and Argentinosaurus are in the ground, enormous and mineralized and patient, waiting for the next team of researchers to arrive with their brushes and their chisels and their imaging equipment and their questions. They are a kind of communication across 66 million years. A message from the world that was to the world that is, saying only this: we were here. We were this large. The world was built around us, and we moved through it, and our feet shook the ground, and our breath was visible in the morning air, and we were real. And in the dark of this night, in the quiet at the edge of sleep, you can feel them, not as ghosts, not as fantasies, but as the deep substrate of the world, the geological fact of their existence pressing up through the rock, through the sediment, through the long uncounted years, to here, to now, to you, to this moment in which you are aware, in a way that you were not quite aware before tonight, of the extraordinary depth of the world's history, and of your own tiny luminous place within it. Sleep now. Let the ground carry the vibration of something very large moving through the dark, Let the mist settle in the low places along the river. Let the long neck swing in its slow pendulum, arc through the cool morning air that is coming somewhere for an animal that does not know it is imagined. That simply is what it is. Enormous and ancient and alive, in the valley beyond the platform, in the tall forest near the river, in the world that the asteroid missed. Where in the world are you watching from? Let me know in the comments. And don't forget to subscribe if you want to see more videos like this. See you on the next one.